Okay, let me show you the contents of this video, which I'm going to cover. First, I will explain what is the Fourier series, and then I will explain the trigonometric Fourier series. After that, I will explain the exponential Fourier series, and then I will cover the MATLAB code to implement the trigonometric Fourier series. And in the last, I will discuss the MATLAB code to implement the exponential Fourier series. Here my main concentration on this part, I mean the MATLAB implementation. Therefore, I will give just brief introduction to the theory part. Okay. So now let us see the basic theory of the Fourier series. In mathematics, it is shown that a function ft can be expressed by this infinite series such as the c1 g1 plus c2 g2 plus c3 g3 and so on till infinity. Here the c1, c2, c3 are actually the constants, and the functions g1, g2, g3 are the functions which are orthogonal to each other over an interval t1 to t2, such that integrating this product, I mean just take any two functions of this family and multiplying them and integrating over that time interval, you will get 0. So it shows the orthogonality condition of any two functions, and if I multiply the signal with itself and then integrating over that time interval, I get some constant. So here the functions g1, g2, g3 are the member of a complete orthogonal set. Okay, now let's see what is a complete orthogonal set. So a set of functions g1, g2, g3 is said to be completely orthogonal in an interval t1, t2 if there exists no other function xt such that this integration becomes 0. It means it satisfies the orthogonality with any member of this set. So if some function xt is found to satisfy this above equation, then obviously it is not called the complete set, as xt also becomes a member of this set. Okay. So as a complete set of orthogonal functions, we have the family of the sine n omega naught t and the cos n omega naught t for n equal to 1, 2, 3 like that. So this mathematical background gives the motivation to lay the foundation of the Fourier series. So now let us see what is the Fourier series. So with a similar pattern, a function ft can be expressed as the linear combination of these orthogonal functions, which are the member of a complete orthogonal set, such that a function ft can be expressed as a naught plus a1 cos omega naught t. So that is equal to your c1 g1 plus c2 g2 plus c3 g3 like that. So a2 cos 2 omega naught t plus an cos n omega naught t till infinity, and then member of the sine family till infinity. So this is how you can express a signal or a function ft into these infinite sine and cosine components. So these components, I mean just such as cos omega naught t or sine omega naught t, etc., these are known as the harmonics. Okay, and this equation can be rewritten like this. So ft equal to a0 plus sigma n equal to 1 to infinity an cos n omega naught t plus bn sin n omega t for the interval t. So here you can see that sigma is varying from n equal to 1 to infinity. Obviously here for this term your n is 1, and this is for n equal to 2 and so on. Okay, and here you can find this a0 by this equation. So a0 is 1 upon t integration t0 to t0 plus t, I mean integration for one time period ft dt. So that means you are integrating your function divided by the time period. So obviously your a naught is the average value of your function ft. So that is representing the dc content of ft if it is present, and this coefficient an can be obtained by this equation, and this bn can be obtained by this equation. Okay, so this equation which is representing ft in infinite number of sine cosine harmonics is known as the trigonometric Fourier series. Okay, now let's see the another form of trigonometric Fourier series, which is known as the compact form. So this previous equation can be simplified and can be rewritten like this. So f equal to sigma n equal to 0 to infinity Cn cos n omega naught t plus phi n. So this sigma is starting from n equal to 0. It means the average value is also included here. So that is obviously the C0 for n equal to 0. And here Cn is obtained by this equation square root an square plus bn square, and this is the phi n, which is representing actually the phase shift of these harmonics by minus tan inverse bn upon an. Now if we can plot Cn and phi n with respect to n, so these plots actually represent the magnitude and the phase spectrum respectively. Okay, the magnitude plot gives the information about the magnitude of each harmonic, and phase plot gives their phase shift information. And now let's come to the exponential Fourier series, which is a very effective representation of the function ft. So besides sine n omega naught t and the cos n omega naught t, we have another family of functions, orthogonal functions, which is the e power j n omega naught t for n equal to 0, plus minus 1, plus minus 2, plus minus 3, and so on. So that is another family of the orthogonal functions, and it's a complete set of orthogonal functions. So obviously your function ft can be represented by the linear combinations of these exponentials like this. So your ft is f0 plus f1 e power j omega naught t plus f2 e power j 2 omega naught t, like that till infinity, plus f minus 1 e power minus j omega naught t, f minus 2, that is a subscript, e power minus j 2 omega naught t, like that till infinity. So in the first row all positive values of n is covered, and in the second row all negative values of n is covered. So if I can express this equation mathematically, I can write this equation. So obviously your n is varying from minus infinity to plus infinity, and fn e power j n omega naught t. So that is your exponential Fourier series. So this is an exponential Fourier series representation of ft in an interval t0 to t0 plus t. Here fn can be found by this equation. So that is 1 upon t integration for one time period ft e power minus j n omega naught t dt. So this is rather simpler than trigonometric Fourier series, where we have to find 3 integrations, and here we have to find only a single integration, that is fn. So it is simpler to compute the exponential Fourier series. Also actually it has the foundation to evolve the Fourier transform. Later I will show you. And now let us see that what is this fn, and what information we can derive from fn. So this fn, which is just calculated, maybe is a complex valued or real valued. It depends on the signal symmetry and the shape. So so you can find the magnitude as well as the phase spectrum from this fn just by this mathematical operation. I mean having the modulus of fn, so that will give you your magnitude spectrum, and then angle fn will give you the phase spectrum. And this magnitude spectrum and phase spectrum actually is similar to the Fourier transform. So whatever shape we get from the Fourier transform, the same shape we get from this magnitude spectrum. So we can say that exponential Fourier series is actually the base for your Fourier transform. We have the relationship between the trigonometric Fourier series and the exponential Fourier series, because the exponential Fourier series expression is directly derived from the trigonometric Fourier series. Derivation I'm not giving here to keep it precise. So we have a few relationship equations. For example, the A0 of trigonometric Fourier series is equivalent to the F0 of exponential Fourier series, and both are representing the average value of your function ft. and you can get the value of an from this equation, summing fn and f minus n, and you can get bn by this subtraction multiplied with the j, and if you have an and bn, you can find fn from these an and bn like this, 1 by 2n minus j bn. So these are a few relationship equations. And this whole analysis is for the continuous time signals. So therefore it is known as a CTFS, I mean the continuous time Fourier series. The same theory can be extended to the discrete time signals as well. So that is known as the DTFS. So now let us go to the implementation of this Fourier series in the MATLAB, so that you can have the better idea that what exactly we are getting from the Fourier series and why do we go for Fourier series analysis. So for that I have implemented both the form of Fourier series, I mean the trigonometric as well as exponential Fourier series in the MATLAB using the Symbolic Maths Toolbox. So this is the program to implement the trigonometric Fourier series using the Symbolic Maths Toolbox. Symbolic Maths Toolbox. Okay, so it's quite easy. First we are getting the user input. The user will enter any function of the t as a string. So for example, you want to enter a function, let's say e power minus t, then user will enter this as a string, like exp minus t. And since it is a string, so it will be converted into the symbolic expression using the str2 sim and then ft. So your ft becomes a symbolic maths expression. Now n equal to input, enter number of the harmonics to be calculated. Since your Fourier series is computing the infinite harmonics, so obviously it is not possible to calculate infinite harmonics for any program or any machine. So you can compute some finite number of harmonics. So suppose if I enter, let's say 5, your first 5 harmonics will be calculated. Okay, and then we enter the t1 and t2. These are your time limits. For example, if you enter e power minus t, then you have to define actually the time limits from where this function is expanding, I mean from t1 to t2 like that. So you have to give these 2 time instances in between your function is defined. So from that you can calculate the time period of this periodic function also. Okay, let's say this is a periodic function. So this is your ft. So obviously the t is calculated, t2 minus t1, and this is your omega, that is 2 pi by t. And here number of harmonics are defined. That means n has the count from 1 to capital N. So if you enter 5, it is 1, 2, 3, 4, 5. A symbolic variable t is declared here, and then these are your 3 integrations which we are computing here. So the first integration, if you remember in the trigonometric Fourier series, that was a naught equal to 1 by t, integration for one time period ft dt. So this integration is expressed here. So 1 upon t integration, this is integration in Symbolic Maths Toolbox. This is your function ft from t1 to t2. These are integration limits, and that is obviously calculating the average value of your function. This is your second integration where you are finding an, that is 2 by t integration for one time period, and ft cos n omega naught t dt. So this is your second integration, and this is your third integration of bn. It's the same expression, but instead of cos you use sine n omega naught t. Okay, so that is your third integration. After that the ann and bnn are calculated, that is an cos n omega t and bn sine n omega t. If you remember this expression of Fourier series, n equal to 1 to infinity, a n cos n omega naught t plus bn sine n omega naught t. So an into cos n omega naught t, that is your a n n, and bn sine n omega t, this is your b n n. So these a n n and b n n are calculated. Average value we are getting in numbers because a0 is in symbolic form. So we are getting in numbers, and then we are defining a time vector for plotting and initializing the an sum and bn sum because sigma is there. So you have to add all the values of n cos omega t and bn sin n omega t. So that's why a for loop is there to add all the values for each n. Okay, so you can see that a n sum is we are getting by adding all the a n n and b n n values, and then we convert into the numbers because a n sum and b n sum in form of symbolic variables. So just by using the eval function, we convert them into the numbers. So a n sum and b n sum are in numbers, and then now this whole expression is computed in this line. The average is also added. So that is your Fourier series. So ft equal to a0, that is average, plus an sum, this is an sum, and this is bn sum. So this is your FTA approx. FTA approx means since we are not computing the infinite number of harmonics, we are computing only the n number of harmonics which are finite, suppose n equal to 5. So what happens, instead of adding infinite number of harmonics, what type of function I will achieve with only the 5, let's say 5 or 10 or something finite number of harmonics. So obviously I will not get ft, I will get an approximate version of ft. So this will give a better idea that what is the effect of adding the finite number of harmonics to synthesize my function ft. So that is will give you a better idea of Fourier series, and here I am getting the average value vector, and then I am plotting all the harmonics. So so harmonics equal to ann plus bnn. So all sine and cosine will be added and will be displayed in form of a plot. And here I am plotting the average value as well as all the sine and cosine harmonics. So in a graph you will see the average value as well as all sine, cosine harmonics which are calculated for that ft. And here we are plotting the actual function and the approximated function. So this is your actual function ft which is evaluated for that time vector t for plotting purpose. So all numerical values will go into the FTO, and with this plot you can see that FT approx, I mean that FT approximated FT with the n number of harmonics is plotted, and this is your actual function FT. So you can compare both the functions side by side. So what is the difference between the actual function and then approximated function? Okay. These are all your title and legend, etc. And here we are plotting the magnitude spectrum as well as we are plotting the phase spectrum. So magnitude spectrum is easy, as you know, this is square root n square plus bn square, and we are appending the average value. So this is just plot using stem plot. We are plotting this magnitude spectrum, and this is how we are calculating your phase. So your theta equal to minus tan inverse bn upon an. So you remember this expression, tan inverse bn upon an, and then the theta we get in the radians, so just converting into the degrees and then plotting these degrees. So here with a stem plot again we are plotting this theta. Okay. So now let me show you the outcome of this program. So this is one function ft which is exponential function e power minus t with a period t. Okay, so your period is 1. So this is the outcome of my program. So here you can see that this is the average value, and these are all harmonics. Here I have used actually the total 5 harmonics. So you can also see the 5 is written here. So you can count 1, 2, 3, 4, 5. So just 5 harmonics when summed together along with this average value, you get this type of function ft. So this is your approximated function ft, and this red one is your actual exponential function, which is e power minus t. So you can see that only the 5 harmonics can approximate the signals like this, which is quite close to your original function. And if you increase the number of harmonics, this closeness will further increase. This is the magnitude spectrum. So this is n equal to 0, means it is your average value. Same here you are getting. And this is your first harmonic, second harmonic, third, fourth, and fifth harmonic. And this is the phase. So this is a 0 degree of DC. Obviously, it's a DC value. And this is the phase, something near about 80 degree, minus 80 degree of first harmonic, second, third, fourth, and fifth. Okay. So this is the outcome for this e power minus t. And this is my second example. We have taken this periodic function sine t from 0 to pi, and this is your average value. All the harmonics are here, and here you can see this red one is actual function and blue one is your approximation function. So they are closely matched with each other. Here we are getting some discontinuity at the end. This is the magnitude spectrum, and this is the phase spectrum. And this is another example, your function ft, which is the t from -1 to +1, and these are all harmonics, and this is the approximation function, blue one. You can see it's matching with your original function t, and this is a magnitude spectrum, and this is phase spectrum. Here you can see that average value is 0. Obviously it will be 0 because this positive area is equal to this negative area. Okay, it's a symmetric, odd symmetric wave. So that's why you're getting this average value 0. So now let me simulate this program in MATLAB, and let me run the same functions there. So let me jump to the MATLAB, and this program is already written. So let me run this program. Okay. So this is asking me to enter any function of t. So I can enter the function, first one, let's say exponential minus t, e power minus t. So I have to enter like this in form of string. Okay. Now it ask me to enter the number of harmonics to be calculated. So let me calculate 5, and the first time limit, that means 0, and the second time limit, let's say 1. Okay, so this is the output which I achieved, and this I have already shown you also in the slides. So these are all your harmonics and average value. This is your ft, red one, and approximated ft, which is blue one, magnitude spectrum, and then phase spectrum. So let me try one more example. And now I can enter, let's say, sine t, and number of harmonics 5, enter the limit 0, and pi, 0 to pi. So let me see what output I will achieve. So this is the output you can visualize. So this is average value, all the harmonics, and ft and approximated ft, magnitude spectrum, and then phase spectrum. Okay, so this is for sine t. And now let me run for another one. So let me any function, let's say t, any function t, number of harmonics. Now let me increase, let's say 10, and enter the first limit 0 and then 1. So let's say what output I will achieve. Okay, so this is the output, and here you can see that all harmonics, your 10 harmonics which you requested along with the average value. And here you can see that as I increase the number of harmonics, the approximation is quite good in this case. Obviously at both ends we are getting more error. That is because of the Gibbs phenomena. At the discontinuities we get more energy concentration. So this is a magnitude spectrum and this is your phase spectrum. Okay, now let me go to the implementation of exponential Fourier series. So in this current program which I have just presented to you, I have not given the facility to enter the functions, piecewise linear functions such as your gate functions, I mean some rectangular pulse train like that. So here I have tried to make a versatile program which can accept all types of functions, whether it's a function of t or whether it's a piecewise linear function, I mean the two-piece function or three-piece functions like that. So here you can see it can cover any function of t, that is a one-piece function, and then it can also accept any two-piece function. Two-piece functions means like this, okay. So this is broken into the two parts for one time period, okay. So 0 to t and t2 plus t like that. And three-piece functions, I mean this type of functions which are described in three pieces, I mean 1, 2 and 3. Also a square wave like this, so which is also in three pieces, I mean from let's say t1 to t2, then t3 and then t4. So this type of functions you can enter. So this program is quite impressive and very efficient and can accept any function of t. So let me explain. So this is a symbolic variable t, and here you have to enter your choice, what type of function you want to enter. I mean if you enter 1, you have to enter a single piece function, and if you enter 2, then you can enter the functions like this, a two-piece functions, and with 3 you can enter the three-piece functions. And you can further expand this code to have a four-piece functions and so on the similar pattern, okay. So now if you enter the choice 1, it means you can enter your function which is a single piece function of t. So you can enter your function ft, which will be converted into the symbolic expression, and then again the number of harmonics to be calculated, and then two endpoints of your function. For example, if you are entering some exponential functions like this, so this is your t1 and this is the t2, and after that we find the time period t2 minus t1, then omega, that is 2 pi by t, and then getting this vector, I mean the number of harmonics. Here you can see that it is from minus n to plus n, because if you remember the expression of Fourier series, your ft equal to n equal to minus infinity to plus infinity. Since we are here we are not finding the infinite harmonics, that is also not possible. So we are finding only the finite harmonics, so minus n to plus n. Okay, so that is your fn into e power j n omega naught t. So that's why this n is declared from minus n to plus n in this line. And here we are finding the fn. So this integration, if you remember, fn equal to 1 upon t integration for one time period, I mean t1 to t2, your function ft, and then e power minus j n omega naught t dt. So this is simulated here. So 1 upon t integration ft e power minus j n omega naught t, and these are integration limits from t1 to t2. And then we are calculating this exponential. So this exponential we are calculating e power j n omega naught t by this line. Then defining a time vector for plotting, and then doing some operation that will be needed in plotting. And then we are getting the actual function of t. Okay, so this is your original function ft. So that will be utilized in plotting. Now this is the code for choice 2, where you enter your two-piece functions. Two-piece functions like this. Okay, so this is your t1, this is your t2, and this is your t3. So you have to enter the function in two pieces. So this is your first part of function ft1, and this is your second part of function ft2. So here ft1, that means input the first part of your function, ft2, that is input second part of your function. And then converting these functions which are in form of string into the symbolic expressions. Then getting the number of harmonics to be calculated, and all these three limits t1, t2, t3 like this. Okay. After that we find the time period, that is t3 minus t1, your omega, and then your n vector, that is from minus n to plus n, to compute this sigma from n minus n to plus n. And then again we are finding this fn. Since your fn is in two piece, that's why your integration is also in two piece. So first integration is from t1 to t2, plus second integration is from t2 to t3. So you can see that first integration t1 to t2, and then second integration from t2 to t3. The same thing you can also append in your first program also, which I have suggested. And here we are computing the exponentials, and then defining the time vector. And this is I have done everything to plot your input function, and to make this program versatile. I mean, it can accept any type of input of t, and it can plot it. So these few lines of code will do that. And this is for choice 3, where function is of your three parts. So it can be like this. So let's say this function is of three parts. So this is your t1, this is your t2, this is t3, and this is t4. So this is your first part ft1, this is second part ft2, this is third part ft3. So you are entering ft1 and entering ft2, then ft3, and then converting all into the symbolic expression, then getting number of harmonics, and then getting all these time points t1, t2, t3, t4, and then obtaining the time period, your omega naught, and then your harmonic vector. Okay, and this is here you are getting your integration in three parts now. So integration from t1 to t2, and then integration from t2 to t3, and then integration from t3 to t4. So this is how your fn is calculated. You can see all these limits, three integrations, and then calculating exponentials. So now plotting your actual functions, again defining the time vector. So this everything is done to plot your input vector, and again we are getting the average value, and then we are getting the approximated function. I mean your ft, approximated ft with the n number of harmonics. Okay, and it is evaluated for that time vector. So all numerical values go here for plotting. So with this plot, we are plotting your approximated function ft approx, and then plotting your actual function ft. So you can compare both with all titles and legends, and then we are plotting the magnitude and phase spectrum like that. So we are checking whether your fn is real or not. If it is real, then we do nothing. Simply we assign magnitude to fn, and then theta degree will be the 0, because fn is real. So obviously the phase vector will be the 0. And if it is complex, then absolute value will be given into the mag, that is a magnitude, and theta will be the angle fn. Okay, and it is converted into the degree from radian to degree. So that will go into the theta degree. So with the help of the stem plot, we are plotting the magnitude with respect to n, and with the stem plot again we are plotting the phase values with respect to n. Okay, so now let me show you some simulation results with this. So again I have taken the same function e power minus t from 0 to 1, number of harmonics are 5. So this is your magnitude spectrum. So here you can see both positive side and the negative sides. So n equal to 0, 1, 2, 3, 4 and 5. This is minus 1, minus 2, minus 3, minus 4, minus 5. This is your phase spectrum. And as I said that this exponential Fourier series spectrum actually creates the base for the Fourier transform. So if you go for the e power minus t Fourier transform and plot the phase and magnitude spectrum, you will get the same shapes for magnitude and the phase spectrum. Okay, so you can say that this is ABCD of your Fourier transform. Okay, like that. And in this graph you can see your ft, approximated function, blue one, and this is your actual function ft. Okay, and let's see one more example. So this is your square function, where this is the case of the choice 2, where the function is of 2 parts. So this is first part and this is the second part in this time interval. Okay, like this. So the first 5 harmonics are computed. So this is the average value. Average value is 0.5. It is quite simple. Since this is 0.5, so 0.5 multiplied with 1 is the area, that is divided by 1. So 0.5 divided by 1 is 0.5. So that is the average value, which is your f0 also. So the first harmonics, and see this second is 0. First is there, second is 0, third is there, fourth is 0. So it means all odd harmonics are there. Okay, and all even harmonics are not present in this case. And this is your phase spectrum, and this is your actual function ft, and this is your approximated function ft bar, which is just with only the 5 harmonics. And if you increase the number of harmonics, these oscillations will reduce. I will show you in the coming slide. This is one example of a bipolar square wave. Again, it is an example of the choice number 2. That means function can be defined into the 2 parts, plus 1 and minus 1. And here you can see that average value is 0. Obviously, this positive area is equal to the negative area. So average value is 0. And again you are getting the odd harmonics, n equal to 1, n equal to 3 and n equal to 5. This is phase spectrum, and this is your ft and approximated ft. This is one more example of a triangular wave. Again it's example of choice number 2. So function is defined in 2 parts, 1 part and 2 part. So this is your spectrum. Okay, and this is a phase spectrum, and here you can see the approximation. So this blue is your ft approximated, and this red one is your actual function ft. So quite close. With help of only the 5 harmonics, your function is quite matching with your original function. I mean, approximated function is quite closer to your original function ft. And let me show you one more example. This is the example of the 3 part, I mean the choice number 3, where your input function is divided into the 3 part. So this is the first part, minus 1 to minus 0.5, that is 0, then minus 0.5 to plus 0.5, it is 1, and then plus 0.5 to 1, it is 0. So your function will be defined into the 3 parts, and you can use that choice number 3. So this is your magnitude spectrum, this is phase spectrum, and here you can see both the functions. So obviously because of this gate function, you are getting a sinc function as the output. If you know the output for a gate function, you always get a sinc function as the output in magnitude. And this is the same function, but here I have increased the number of harmonics from n5, I have it increased to 50. So you can see that the approximation is much closer to your original signal, but at the discontinuities you are getting the more oscillations, and that is if you know what is Gibbs phenomena. So that is actually clearly showing your Gibbs phenomena where more energy is concentrated on the discontinuities. Okay, so now let me run this program into the MATLAB, and I can show you that how you can run this program. So this program is already here, so I will simply press this run button. So now it is asking me my choice, enter your choice. So obviously first I will enter the first case where I can enter a single piece function of t, any function of t. So I can enter, so let's say I can enter exponential minus t, so that is e power minus t, and the number of harmonics to be calculated, let's say 5, first time limit 0, second time limits let's say 0.5, and let's see what output I will achieve. Okay, so this is the output which I'm getting. So this is my magnitude spectrum, phase spectrum, and this is my ft and ft bar. So red is your actual exponential function, and blue one is your approximated function with only 5 harmonics. Okay, now let me try the second choice. Okay, let me try the second choice. So choice number 2. So it is asking me to enter my function in 2 parts. So first I have to enter the first part. So let's say 1. So here I am giving a unipolar square wave, and second part is 0, and harmonics let's say 5, first time limit 0, second is 0.5, and third is 1. So let me see the output. Okay, so this is the magnitude spectrum, and this is the phase spectrum, and this is the output. So your red one is your actual function, and blue is your approximated function with just 5 harmonics. If you increase the number of harmonics, the approximated function will go more closer to your original one, right? Now let me try one more. I can enter the bipolar one. So the first part is 1, second part is minus 1, and number of harmonics let's say 5, first time limit is 0, then 0.5, and then 1, and this is the output. So here you can see the average value is 0, obviously because it's a bipolar square wave where positive and negative area is same, and this is, you can see, your approximated function along with your original function. And now let me try one more. I can try one triangular periodic function. So enter choice 2, and the first part is obviously the t, second part is minus t plus 2, and number of harmonics 5, first limit is 0, 1, 2. So I should get a triangular wave. Okay, so this is the magnitude spectrum, and this is the phase spectrum, and yes, here I'm getting a triangular ft and approximated ft with the blue. Okay, just with the 5 harmonics. Now let me try the third choice, which receives the function in 3 parts. So choice number 3, and enter any function of t, first part. So let's say this is 0, and let's say next is 1, then 0 again, number of harmonics let's say 10, first limit is let's say minus 1, second is minus 0.5, then plus 0.5, and then 1. So this is your gate function, which is at t equal to 0. So you can see, so this is a gate function which is centered at t equal to 0. So here 10 harmonics I have taken. So see this approximation, and this is the magnitude and phase curve. So it's your sinc function. Okay, so it's your sinc function. Okay, let me try one more function, just some random function, and let's see what output I will achieve. So let's say first part is the t, and second part is minus t plus 1, and harmonics 5, 0, 1, and 2. So this is what I'm carrying. So this is your approximated function and your original function ft and f mar t, and this is the corresponding magnitude and the phase spectrum. Okay, so this is how you can use these two programs to find the Fourier series of any function. You can go for trigonometric Fourier series as well as you can go for exponential Fourier series. So I hope that you have learned a lot of things with these programs, and I suggest you to take your textbook of signals and systems and just take any question from there and just try to solve that question with this program and match that theoretical answers with this outcome of this program. So I really thank you all for watching this video. Please like it, share it, and stay tuned for more such interesting videos to come. So till then, goodbye.